is Christian Dawit. I learn in International Leadership Academy of Ethiopia, and I live in Ethiopia, which is found in Africa, and I'm 16 years old, and I bet every one of you know your age, and today I bet you are going to be interested in calculating the age of the universe, and today we are going to calculate the age of the universe. Scientists say that there are three types of universe: open, closed, and flat. Open universe, it will expand forever, and there would be no stop, or there would be no limit to its expansion. Closed universe, it would expand, and it would collapse on itself. And the other type of universe is flat universe. This is what scientists say that our universe is, and its total energy is going to be energy will be zero, and it will continue to expand because in an exponentially slow rate, and it would stop expansion when time reaches infinity. If we are sure that our universe is expanding, let's see as this electrons, for example, this is on high energy level, and this is on low energy level. This high energy level, when it drops out, according to Planck's theory, it would release photon, which causes light. So the color of the light would be blue, and the low energy, when it drops out, it also gives photon, the color would be red. Let's compare the blue and the red. Blue, since it's on high energy level, it would give high energy. It would have high frequency, and it would have short wavelengths. The red one, low energy, low frequency, and long wavelengths. So the blue one, it would be the opposite of the red one. To calculate, we know this old formula, which is velocity is equals to distance over time, and we can rephrase this as time is equals to distance over velocity. So to calculate our time, we have to have the distance and the velocity. Let's see how to calculate distance and velocity. Distance. If say this is our if this is our Earth, and if scientist X and if scientist Y are observing a galaxy Z, it forms a triangle. So using this triangle, we can calculate the distance. Let's say this is D. This is what we want, D, the distance between our Earth and the galaxy Z. And this is theta. So theta would equal to xy over xz. Xz is approximately equal to this distance that we want. So we can xy over d. So we can rephrase this, and d is equals to xy over theta. This is how we calculate the distance between our different galaxies and stars. Velocity. First, we have to know about, let's talk about Doppler's effect. For example, when an ambulance is approaching us, we would hear a lot of noise, and then when it's going away, we would hear a low noise. Let's this be us, and if this was the normal wavelengths, this would be a wavelength when it comes near. So when it comes toward, we would have high pitch and high frequency. And let's say this is the normal wavelengths, and when it's going away, we would see that the waves expand. So away, it would be low pitch and low frequency. So using Doppler's formula, we can calculate the velocity. First, if this is the light that we get from galaxy, let's say Andromeda, and we would pass it through the prism, and it would give us a spectrum. This spectrum It's like how rainbows form. The rainbows would disperse, and we would see the different colors. And these black lines, they represent elements that are found in that galaxy or in that stars. So since we have those elements on our Earth, we can simulate it, and we would get kind of like this graph. So we would see that the lines have been shifting a little bit more. So if we see it after a little bit more time, we would see that they have been shifting. So then if this is the first time we see it, and if this is the second, the third one would be. So every time we see it, it would go further. So this means they are going away from us. So let's calculate the velocity. According to Doppler's law, distance, velocity over speed of light is equals to difference in wavelengths over wavelengths. So we can rephrase this, and velocity is equals to difference in wavelengths over wavelengths times speed of light. Hubble's constant. Hubble was the one who came up with this formula. Let's say this is a line, 0, 1, 2, 3, 4, and 5. If the distance between 1 and 2, let's say A. And the difference, for example, if we want to calculate the difference between the distance between 5 and 1, we would subtract 5 minus 1. So distance would be change in x times A. Since our universe is expanding, A would be expanding at the relation with time. So let's differentiate with time over the differentiation of t, different in x times differentiation of A over differentiation of t. Distance over time is velocity. So velocity is equals to distance x, and this one is A dot. It's a convention times A dot. And we can multiply this by A over A. It's as multiplying as by 1 because it will cancel out. So velocity is equals to change in x times A dot over A. This one we have stated that in earlier that it's equals to distance. Velocity is equals to distance times, this is what we call the Hubble's constant. So to get Hubble, we would get velocity over distance. The Hubble's constant is said to be 72 kilometers per second per megaparsec. Megaparsec is an astronomical unit which is used to calculate distance. So 1 megaparsec is equals to 3.26 times 10 to the power of 22 meters. 72 kilometers per second, since it's we can reciprocate, and it could be the reciprocal of it in second times, it would be 3.26 times 10 to the power of 22 meters. 72, when we divide 72 by 3.26, it would be 23 times 10 to the power of 3 meters. 1 kilometer is 1,000 meters, so 3 times 10 to the power of 22 meters. Meter will cancel out by meter, and this would be 23 over second times 10 to the power of 3 minus 22, it would be 90. So we can say that 2.3 times 10 to the power of 18 second minus 18 second. This is the Hubble's constant. And we have stated that time is equals to distance over velocity, and Hubble's constant is equals to velocity over distance. So 1 over Hubble constant is the time. So to calculate the time is equals to 1 over Hubble's constant. We have found that 1 over 2.3 times 18 seconds. Since it's hard to know by seconds, we would multiply it by year, and 1 year is equals to 31,536,000,000 seconds. So we can 1 over 2.3 times 10 to the power of 18 times 31,536 million years. We would get 1 over 72,532.8 times 10 to the power of 15 years. So when we calculate this, we would get 13.79 times 10 to the power of 9 years, which is equals to 13.79 billion years. So if any one of you have a question or don't know your age, come to me. Thank you.